Maybe this is the last lecture for the long channel MOSFET, and I would like to move to the third part, the last part, the short channel MOSFET. Hopefully, okay. Let's go to this way. Uh, Up to now, we have thought about how can we evaluate or predict the IV characteristics of our transistor MOSFET. Of course, we have to understand this one. Here we have four-terminal device called as MOSFET. So we have to also describe four different terminal currents. Here we have source and drain, and here we have a substrate, or sometimes called as a body, and here we gate. And up to now we just describe the current called as drain current. Of course, its polarity just looks like this. So the current flowing into the device through this drain terminal. We have thought about this quantity almost exclusively, and we have not thought about how about the gate current, or how about the source current, and how about the body current. The reason is quite obvious, because in this case we assume that this gate, the metal gate, is perfectly isolated from this channel by this very good dielectric layer, so no current is allowed. So from its assumption, so gate current is always equal to 0 in an ideal case. Of course, I'm saying that this is in an ideal case. And another one is, of course, we have to also consider the body current or substrate current. And if you ask me, is this really 0 or not, then of course I have to say that this is non-zero. But when we make a comparison between the absolute value of ID and IB, then certainly we can say that ID is in many cases much larger than IB. So compared with this drain current, in many cases body current is negligible. Then the remaining one is the source, and in this case, what we have to do in reality for this four terminal device is actually sum of four terminal current should vanish. This is a law, physical law. We must have 0 current, but we have assumed that this is almost 0 due to the perfect isolation. And also this where do we have a body? Yes, let's say that this is a body current, and this is much small, although not exactly 0, but this is quite close to 0. So from this relation, then we can say that source current should be almost negative of drain current. So that's the reason why we have concentrated on only on this drain current. If you are asked to answer the source current, then from this argument you have to say that this is the expression for your source current. And unfortunately here we have no idea about body current, but this is also another story. Okay, so let's just get started in today's lecture. Up to now we have assumed that our mobility can be expressed as a certain quantity called as mu effective mobility, and we thought that this can be just pulled out from this kind of integration. So when we first start, we start from more general expression. This W is considering the width direction, z directional width, and here we have mobility, which can be position-wise quantity, and also electron density, also position-wise quantity. Also here we have driving force for this current conduction. If you remember correctly, actually in this place, instead of this V, actually we have to introduce this point-wise electron quasi-Fermi potential. But in this MOS structure, we had a really good approximation, like this one can be well approximated as, so just V channel potential, which is solely dependent on Y instead of this depth direction X. That was the trick. We make it much simplified. And when we consider this one, here we have a vertical directional integration, dx integration, and this one. Both of them, mobility and electron density, are functions of x. Vertically, they can have different values. However, here, in this case, we just pull out certain quantity. If we are really rigorous, then actually we have to also include here mu sub n. Electron density should be integrated with this weighting factor of the electron density. But we are just now doing certain trick, like a magic. Here mu, and here we have n, but just saying that we have only n here. So don't be pulled by this trick. This does not comes free. In order to make this kind of expression, we have to define what is mu effective and how can we must check whether this kind of assumption is valid or not. If we introduce a very strange value for mu effective, then of course this equality does not hold. But if we define our effective mobility in this way, then actually this equality becomes just an identity, because just put this definition into it, and you can find that actually this upper part survives, and this lower part exactly cancel out this one. So it just recovered into the exact expression. So this is nothing but just to introduce a new notation, and this expression is exact as much as we define effective mobility as this expression. Seemingly quite complicated, but please have a look at its expression. Here we have upper part and lower part. And lower part, you can see that electron density is vertically integrated. So if we just express it in our plain language, then we can say that this is areal electron density. This guy, electron density itself, is actually per cubic centimeter. However, we just integrated over vertical direction, so we have just quantity of per square centimeter, per unit area. How many electrons are found? That is information taken from this one. This is easy to understand, but when you have a look at this upper part, the integrand is no longer just electron density. It is the product between electron density and mobility. So then we will have a very strange quantity, but eventually that is once again divided by this integrated electron density. So by doing this action, so you can immediately understand at least the dimension, surviving dimension, is only the one by mobility, because the lower part doesn't have mobility and upper part has the mobility, and all other dimensions are cancelling out upper and lower part, and we have a certain quantity corresponding to the mobility. And let's assume, for example, this kind of behavior. This is vertical direction, and let's say this is our electron density. And electron density, in many cases, electron density in our assumption rapidly decreasing when we go to deep substrate. And now let's say our our mobility happen to be have a certain behavior. So this is just an assumption. Let me just make an assumption like this one. Let's say this is our mobility, and this blue one is corresponding to our electron density. Then if we perform this tower equation 5.50, then what will be the value of our evaluated effective mobility? Who decide, or which quantity decide the effective mobility? You can immediately understand the answer should be the value at this point, because this electron density is used as a weighting factor for this averaging procedure. And here we have nearby this interface, we have a strong preference for the quantity in this case. Although we have certain values, relatively high mobility value, but there is no electron at all. So therefore that does not contribute to our averaging case. So simply speaking, by performing this this expression or evaluation, we can detect the mobility felt by the most of our electrons. Majority of electrons feels 100, and very small number of electrons feels, for example, 1000. Then what will be the average? The average will be quite close to just 100. This is the meaning of this expression. We just take weighting factor, gives the strong preference of a highly populated position. So are you all with me? So in this case, we can easily understand the electron mobility in deep substrate doesn't matter. Actually, that doesn't play any role in our effective mobility calculation. Only the place where most electrons are found, that is important, and that is just within a few nanometer from the silicon and silicon dioxide interface. Then you can ask me quite naturally, ask this question. In this discussion, we have assumed that electron mobility is a function of position x and y. Then how can we assume the position dependency of this electron mobility? They are electrons, but why do they have different mobilities at different positions? It means that I'm saying that currently, if we have a certain device, and this device is several micrometer thick, then in this point we have a relatively low mobility, and in this part we have a relatively high mobility for our electrons. Position dependency. Who makes this position dependency? Who decided this position should be regarded as a low mobility part, and other part is a relatively high mobility part? Okay, so therefore, the question is why mobility is position dependent. We are now saying that along this vertical direction, we say here usually we have a higher mobility, and if we go to this close to the oxide, we say relatively low mobility is found. People have thought about or investigated this issue quite a long time, several decades ago. Actually, it is now known why we have this kind of position dependency. But among many different mechanisms, the most significant in our MOSFET device is actually rough surface. Rough surface means that this figure is taken from a reference paper, and this is a TEM image of a silicon dioxide and silicon interface. Where can you find the silicon? Here you can find the silicon. And where can you find the silicon dioxide? Yes, here you can find silicon dioxide. And now you can see that there is a certain layers of yes, this is corresponding to the most upper part of silicon layer. And if everything is so perfect, then beyond this point we have to have actually amorphous silicon dioxide. But this line, the line written or drawn by the authors of this paper, just shows that seemingly the interface between silicon dioxide and silicon. If you ask me how did they make such kind of lines, I have a little idea about it because so can you make without this already drawn line, can you make a clear distinction between silicon and silicon dioxide? Well, it is a little bit difficult, but anyway, you can see that if everything is so perfect, then you will have just a horizontal line. But you know, in this case, you can see that this seemingly interface are fluctuating up and down and up and down and up and down. So although we have thought that there is a silicon, and on top of it we can introduce a very high quality and very thin silicon dioxide layer, but in reality its surface is not perfectly flat in the atomistic case. Of course, you know, this is the length scale of 5 nanometers, so therefore this fluctuation of this interface is really small. Orders of angstrom range, 0.1, 0.2 nanometer, that is the fluctuation we are currently seeing, but that can introduce some differences. Maybe you can think about it in this way. Well, although our electron inversion channel thickness is quite thin, so small, so it is around orders of a few nanometer, 3, 4, 5 nanometer. Within that short range we can find the electrons. Yes, and now we are now looking at the non-flatness of or roughness of a silicon surface, and this is just orders of 0.1 nanometer. Compared with this 3 and 4, still 0.1, 0.2, that is non-zero, but less than less than 10%. So is it really makes a big difference or not? So that can be your question, and the answer is, in terms of collecting electrons, number of electrons, that is not that much significant. So we can think that amount of electrons collected in this layer can be more and less, I'm saying that more and less similar. But problem is, let's say from the viewpoint of this MOS capacitor layer, we can think about electron gas. So these electrons feels that this is the boundary between silicon and silicon dioxide. So now electrons, when we apply certain electric field horizontally, then they should move toward this direction, the drain, toward drain. And let's say that these electrons are moving into this part where we have slightly recessed or changed boundary here compared with this original one. Now we have a very slight change in silicon dioxide interface. That is actually not that far away, just 1.1 or 0.2 nanometer away. But problem is, in terms of collecting electrons, that is not that big deal. But from the viewpoint of these electrons, they feel that previously they thought that this is the starting point of their occupancy. Okay, I'm now occupying this position, and now when it is moving into this part, and actually this starting point of electrons population must start from this one. So therefore, now think about this case. You are now riding a bicycle, and you are now riding a bicycle, and the road is just flat. So you are feeling quite comfortable with this eye. But let's just say that at a certain position, now you have, although this part also we have a similar load. However, at the interface we have a slight misalignment of these two loads. Then what will happen? So the natural thing, quite a comfortable thing in this original position is no longer attached to this case. Actually, our electrons should its position up toward this interface, because there is now newly available position. So simply speaking, although it's moving in this channel direction, but now let's say that I'm doing in this way. Here we have a wall, and I'm moving in this way. I'm blind, and I can feel this way. This is the electron motion, and when my hand touch the blackboard, I feel quite comfortable, so I can move in this way. But let's say that due to the roughness of this blackboard, happen to be there is such a hump in this blackboard, then what will happen? I'm just proceeding with this pushing my hand, and just feel there is no blackboard at all, and my motion is sometimes when we have a roughness, then I feel certain drastic changing of my vertical motion. So that's the reason why our electron gas here should feel certain mechanism to push it toward this direction. So if it is just flat, then my motion is just determined by this directional, horizontal directional mechanism. But if we have rough surface, and due to the existence of this rough surface, sometimes we feel certain disturbance for smooth motion along the channel direction. That's the reason why now in this case, when we have a rough surface, every time we feel this roughness, then electrons are disturbed from its smooth motion along horizontal direction. So this is the main physical mechanism to introduce reduce the mobility. Okay, so it can have a quite significant role in this position. However, electrons located deep inside in this position, actually they do not feel this kind of roughness, because in this position already it was not occupied by electrons, and slight change in far away doesn't make a big deal. So that's the reason why our electron mobility is heavily affected only nearby silicon dioxide interface. Okay, so are you with me? So that is the physical origin, or I think that this is not that much rigorous discussion. I'm just convince you can qualitatively understand the behavior, so we need more rigorous treatment. But anyway, you can feel that this is the main mechanism to reduce electron mobility. So now you can understand this way. Let's say this is silicon dioxide and silicon, and if our electrons are located in this way, then maybe they do not feel much of surface roughness, but happen to be, instead of this electron distribution far away from silicon dioxide, let's say we introduce this modified behavior of our electron density. Then what will happen? Now this electron gas will feel much more about the surface roughness, and if it is approaching toward this silicon dioxide further and further, it strongly feels that, oh, the surface is so rough and I cannot move quite smoothly. Therefore, you can easily understand this. The overall mobility felt by our electron is really related with its how can I say, average position. If this average position is far away from interface, then there is almost no impact of surface roughness. However, if we can pull our electrons quite close to this silicon dioxide interface, then that will make a severe degradation of our electron mobility. So please think about this one. Already we are saying that our electrons are quite close to the interface. From starting point, we thought that. But when I say close or far away, in every case, they are just within 3 or 4 nanometer away from the interface. But we are now talking about even finer resolution for their average values. If they are placed in about 2 or 3 nanometer away, it's okay. But if that is close, that distance, then it will feel quite a severe degradation. So the reason why I'm saying this one is, this is the reason why we have electric field dependency. So why do we have electric field dependency? Actually, electric field itself is not the driving force to reduce our electron mobility. Our electron mobility is reduced because our electrons are pushed back to its interface, silicon dioxide interface. Then which mechanism can push our electron toward this interface? So this strong electric field can introduce steeper potential well for our electrons. So you know, this is just a part of our Venn diagram, EC and EC of silicon dioxide and silicon resin. And if we have a relatively low electric field, then our potential well just looks like this. But if we increase the magnitude of electric field, then our potential well gets more steeper and narrower. As a result of this narrowing, so our electron should be found in this place. Previously, it can be found in this place. So average or the most occupied position of our electrons gas is quite close to this interface, and that is the reason why our electron mobility, our effective mobility, is a function of effective electric field. Please understand, there is no direct relation between them. There is a hidden factor, so that is distance distance, average distance from the interface. By increasing effective electric field, we can decrease our distance, electron distance from interface, and reduce the distance just to degrade our effective mobility. So although this is the mechanism, but we cannot detect actually the real distance from the interface. This is a non-measurable quantity to us, so we just make some empirical relation between effective mobility and effective electric field. So when we do it, then this is the result. This is a really famous result, and here we have effective electric field, and here we have effective mobility. As we have discussed, if we have high electric field, electrons are pushed back to silicon dioxide interface, and it is expected that mobility decreases quite rapidly. Where can you find it? Actually, here you can find it. When we increase effective electric field, our mobility degrades quite significantly. This part is quite severe for our so-called surface roughness scattering dominant region. Then of course you can ask me this question: is this part is really relevant to our MOSFET, or just an extreme case? Unfortunately, when you turn on your transistor and when you try to get your own current, actually your mobility are placed in this part. So please try to read the number. What is the number of electron mobility? In this case, you can find that 200, 300. You are quite lucky to have this number. But when you study your bulk electron mobility in silicon, the number you have seen was about 1430. That was the value in our quite high quality silicon electron mobility. So compared with this bulk value, you can find a significant reduction of your effective mobility. That is understandable, and this is really unavoidable. So therefore, please do not overestimate your mobility. My lesson to you is mobility is particularly very difficult to increase. Actually, mobility, sometimes people say that mobility is assumed to be 300 or 200 something. So if you assume within a reasonable range, then it's completely okay. But do not say that we can achieve 1,000, 2,000, 10,000. It's not possible at all. So there is a strong dependency on electron mobility and effective mobility. So then what are they? Here I have drawn certain lines. So this is, I guess that this is corresponding to this one. Here we have 1,000, and here we have here we have 100. 10 times difference, and here we have 0.02 as an electric field, and here we have 0.2, so also 10 times difference. So if we make a diagonal line connecting these two, so sorry, maybe my drawing is not that much straightforward, but this is anyway, this is corresponding to the relation like this. Mobility, effective mobility is proportional to the inverse of effective electric field. If that happens, then you can find this straight line. And please try to find out the one corresponding to 1 over effective field. So can you find it? So which one is the most suitable for this description? Maybe this one. This one is corresponding to inverse of effective field. Then what is this? This guy, it shows even steeper reduction of our mobility with respect to the effective electric field. And I remember that this is drawn as just a square of effective mobility. And point is, when you have a look at the behavior of your electron mobility, please try to draw certain line. You can make eye guidance for your drawing, and when you draw it, then let me just do it together. Maybe this is the line. Am I right? So I'm trying to make the parallel shift of this line from this line, and you can see that certainly the behavior of our electron mobility shows even steeper line than this effective mobility. So it is known that electron mobility in its final behavior is quite close to the inverse of a square electric field, and this one is corresponding to the whole. So this is a more moderate variation is obtained. Mobility is always on headache of a MOSFET, because when we try to make a transistor, mobility is not that high. However, don't be too much frustrated, because compared with different material technologies, of course the numbers like 200, 300, sometimes it is not that high, but it is also way higher than some other technologies. So other technologies actually none of our interest at all in this time, but this slide is very important. So the previous slide, in this slide we have shown very famous curve, and actually it has its own name. This curve is so famous and it has its name, and this is called as universal mobility curve. This is the name of this famous curve. When we draw our effective mobility as a function of effective electric field, and the consequence is now we have seemingly one line. Maybe you can feel a little bit strange, because there are so many lines. Yes, there are so many lines, and actually these dots are taken from experimental data. So the direct evidence of universality of this relation was proved by Professor Shinichi Takaki, who is currently previously at Tokyo University. When he was a postdoc, I'm not quite sure he was a postdoc or employee of a certain company, he made this very ambitious comparison. Collect so many wafers from all over the world, from USA, from Japan. At the time, unfortunately, Korea doesn't have a facility, and collect wafers from Europe, and collect many of them independently, and measure this mobility and effective field relation. So in his original paper, when we have a look at the collected data, although they are fabricated by different continents, different fabs, different companies, they all match to this one single line. What is one single line? Means that here we have branches. We do not care about this branch, but instead of that, we can find one envelope. So please try to find out one envelope. Envelope here means that one line and change its slope and one line. This line is common for every MOSFET. If you make MOSFET, then you must have this relation. That was experimentally proven. And also whole case, you have also one line, and here you have another line. Combination of two slope curves. This is the meaning of universality of your effective mobility. When we draw our effective mobility as a function of effective electric field, they should be aligned to the universal curve. Of course, you can easily deviate from this universal curve when you make mistakes. So when you make quite a bad device, then you can reduce your mobility quite a lot. This is quite easy. But at the time, it means that that was the best of a human being. If you can make a best device, then your mobility is limited by this universal mobility. You cannot exceed that value. That was the one we understood in these graphs. Okay. Of course, this is quite specific to silicon and silicon dioxide case. And at the time, everybody was fabricating their device with silicon and silicon dioxide. So that was quite universal. Okay, it means that there is a certain upper limit of our MOSFET performance. Our MOSFET mobility cannot be improved any further. That was understanding. But nowadays, this is no longer the case. Universality is no longer valid to our state-of-the-art device. The engineers did this trick to make boost on their electron mobility. Simply speaking, although I will not consider all the detail of this trick, by introducing strain effect, then simply speaking, we introduce a slightly modified lattice structure or crystal structure of silicon. When we do not push it so severely, then there is a certain structure, atomic structure of our silicon. But in this case, we intentionally introduce certain directional force to our silicon material. And when we do it in a clever way, then it is known that our mobility, electron mobility, can be increased significantly. So therefore, let me just introduce the statement taken from our textbook. Overall, nowadays, the VLSI industry has utilized strain. Strain means that the change of our atomic position due to stress to gain about 10 or 20% on ion current of M MOSFET. This is huge. Even 50% or more for ion of P MOSFET. So that is the real situation. It means that although we are talking about the silicon MOSFET, but the silicon we are currently using in the mass production is not just silicon, just normal silicon. They are intentionally engineered silicon. Then how we can make that engineering by placing certain materials nearby silicon, then we can just expand it or compress it. So that is the way we change the electron or hole mobility. This is typically important for our P MOSFET hole based transistor. So maybe, for example, let's say think about this one. When you study your microelectronics course or a different circuit design course, maybe in the textbook you saw that actually we, in order to make a very good inverter, we have to introduce some unbalance between N MOSFET width and P MOSFET width, because P MOSFET drivability is lower than that of N MOSFET. So therefore, in order to compensate that difference, we have to introduce a wider P MOSFET. So maybe, if you remember correctly, the typical value we have studied in our previous course is 2 to 1. So our P MOSFET should be approximately twice wider to match the driver current. However, that was the case of our planar MOSFET, and nowadays, they have really almost comparable mobility values between MOSFET and P MOSFET. It is because, previously hole mobility is much lower than electron mobility. But when we introduce this strain effect, of course, electron mobility is improved. At the same time, hole mobility is improved. Point is, improvement of hole mobility is much severe than that of electron mobility. So therefore, they are becoming really comparable. So this is actually one of the most important effects we are considering to boost our electron or device performance. So this is a really non-negligible effect. Okay, so I think that this is the end of the content about 저걸 좀 꺼주실 수 있을까요? 저 불, 노란색 불이 무엇일지 한번 네, 고맙습니다. Okay, so this is the end of our discussion about long channel MOSFET. And now let's go to our last part, short channel MOSFET. And actually this short channel MOSFET is the real MOSFET. There is no long channel MOSFET in these days. So we'll just have a look at this one. Previously, when we start our MOS long channel MOSFET discussion, we have thought about a channel length about we have another one. 이건 꺼주시겠어요? 하나만, 저 하얀색 하나만 켜고 합시다. 그 제일 위에 있는 걸 꺼주시면. 네. Okay, so previously we had 1 micrometer long device, and that was regarded as the typical example of a long channel device. And without changing any other parameter, technological parameter of a transistor, in this example, the only change is this channel length or gate length. So previously it was 1 micrometer, and now we introduce just 50 nanometer long device. So let me just give you the comparison. Here is the comparison between these two devices. This is 1 micrometer case and this is 50 nanometer case. You can see that yes, they look why don't you try just in a dark room? So I see that this changing, blinking light distract your concentration. So let's just go in this way. 이건 우리가 어떻게 할 수 없는 일인 것 같은데요. 이거는 우리는 끌 걸 다 껐는데도.
근데 그 밖에
네.
인식하는 센서등이랑 얘랑 왜인지 모르겠는데 연동이 돼서 지금
예.
밖에 사람이 지나가면 이렇게 켜져요.
그렇군요. 누가 한 사람이 이렇게 막고 있다가 퍽퍽 때리기라도 해. 자, 참 온갖 고난이 다 있군요. 수업을 하는데. 자, 알겠습니다. Okay, so this is a 50 nanometer case, and there is no difference between them except for this channel length. And let's just have a look at their performances. So if we remember correctly, actually ID follows the free factor like W over L. Of course, I just took the same W value. Then if we introduce 20 times shorter channel length from 1 micrometer to down to 50 nanometer, we have make twice 20 times shorter channel length. Then we expect just 20 times higher current. That's it. If we just accept long channel description of our IV characteristics. But everybody know that this is not the case. So here, when you have a look at their input characteristics, so of course here we have a long channel case and one short channel case. Well, looks good because we expected 20 times increase of drain current, so seems to be that is quite high. So is it really 20 times, or I have a little idea about that, but anyway it is increased. So simply speaking, there is one good news. When you make your device shorter, then you can just get higher current. Everybody try to increase our own current as much as possible. Just 1% or 2% increase in our drain current or own current is regarded as a real big deal, and they really wanted to increase it. But we have the strong way to increase its own current, just to reducing the channel length. And at the same time, even better news is now we can reduce the consumption of silicon area. Oh, it is really too good to be real, but fortunately to all of us semiconductor engineers, this is true. So if you can make your device smaller, then automatically you can get higher performance and of course reduce the area consumption. It means that this small area means that at the same time you can increase number of transistors integrated in your chip. So it means that now 1 year ago you designed a chip, your chip performed a certain job, but now you can sell another chip which have more capability to your customers. Then your customers feel that, oh, that industry gives us every year much improved power and also capability for doing this job and that job. So that is the magical point of a semiconductor industry. So I think that this is really a rare case in among entire industry. Please think about another different industry. If you spend less resource, you can get better performance. Can you expect such an industry? For example, if you make your car as small as possible, then your car gives us a better performance. Usually, this is not the case. The other way around. Also, if you spend less ingredient for your food restaurant, you can get even higher quality of your food serving. Usually this is not the case. But in our semiconductor industry, fortunately, if we can reduce the size of our transistor, well, we can improve performance and also provide more transistors within given area. Okay, so therefore, everybody wanted to introduce a smaller device, but good news does not hold ultimately. So this is the key. Actually, if I have to once again summarize our entire semester, we can introduce 3 different words. First, you must understand MOS capacitor. Second, you have to understand the behavior of a long channel MOSFET, and that is well given by Pausa double integral. And third one is, but channel reduction is stopped by this effect, reduction of VT. That's all. And we must solve this problem. That's all for our entire semester. So please have a look at this graph. Here, I have prepared 2 different devices. Of course, they are taken from 2 different devices, 1 micro long and 50 nanometer long. This is corresponding to 1 micrometer, and this is corresponding to 50 nanometer. And please note that although they are drawn as if they share the scale, this one shows just 18 microamp, and this is corresponding to a 300 microamp. Okay, so they have certainly quite a different scale, because this one is 20 times shorter, so we can expect almost 20 times higher current in this case. So you can see that one thing you can immediately understand is, okay, this is maximum value is about 18, and the maximum value is slightly lower than 300. So already it is deviating from ideal 20 times higher current. It is increased 10 something times, not exactly 20, but this is not the real effect. Of course, the increase is slightly lower than 20. More important one is this one. Here I have drawn this dashed line. This dashed line is not the real data. The real data is this brown curve calculated from our computer simulation. So we believe this is the correct one. And from this one, this dashed line is introduced just to guide your eyes. What is it? This one is calculated from this way. Here, when you have this ID versus VGS curve, then usually you have certain curve, but usually this is the ideal one because this line is so straight. In reality, this line shows more realistic behavior of course below threshold voltage there is nothing, and when we turn on our transistor, oh, there now we have certain current conduction. But eventually when you increase your gate voltage too severely, then effective electric field becomes too high. That introduces reduction of your transistor mobility. So therefore now typical curve just looks like this. Here you start from a straight line and eventually the slope becomes degraded. Where can you find it? Here you can find it. Here your slope is much lower than the slope found here. Why? The main reason is degraded your effective mobility. This one is corresponding to high effective field. So therefore, when we try to find out or estimate the threshold voltage, usually we wanted to find out just counting numbers. Who decides threshold voltage? Mobility is nothing related with threshold voltage. Threshold voltage is nothing but whether we have a sufficient number of electrons collected in our MOS cap or not. That is the quantity of our interest. So therefore we wanted to kick out this part because its behavior is already severely affected by effective mobility. So we wanted to kick out this one. Instead, we wanted to find out the range where electron density shows the most significant effect. Where can you find it? Here you can find it. In this case, you have almost straight line in your IV characteristics. It means that in this area, increase of your electron density is the dominant factor, and decrease of your effective mobility is not that severe. So therefore, now you can see just motion or behavior of your electron density. Okay, so from this point, you wanted to find out or estimate the threshold voltage. So simply speaking, when you have this IV characteristics, the one way to estimate threshold voltage is try to find out the maximum GM value. You know what is the GM, transconductance, the gradient of your drain current with respect to the gate voltage under a given fixed drain voltage, and try to find out the maximum GM value. And where do we have this value? About 0.7 volt. Then starting from this point, just draw GM line. This slope is corresponding to maximum GM. And when it reach at vanishing current point, and this one is regarded as threshold voltage of our transistor. Of course, usually we do it with quite a small value of drain current, drain voltage. Therefore, usually this impact of drain voltage can be minimized. This kind of approach or extraction method is typically called as GM max method, and it was previously quite frequently used to estimate threshold voltage of our transistor. But nowadays things are a little different. But anyway, this is one way to estimate threshold voltage. Maybe you can ask me this question. Well, we have studied so rigorously about the definition of threshold voltage. Threshold voltage is given by flat band voltage and 2 times 5 plus some blah blah blah. Then why we have to calculate threshold voltage in this way? Although we have a very beautiful idea about the definition of threshold voltage, but it is not that easy to measure it. How can you measure your 2 times 5b? How can you measure certain things? And who knows? There are so many different effects inside your real device. So therefore, we need certain way to extract it from the measurement data. And from the measurement data, this is one way to estimate threshold voltage. But anyway, I just sketched what is the GMMax method, and following this GMMax method, for this long channel device, you can see that estimated threshold voltage is about 0.45 volt. And the same case with shorter device, 50 nanometer case, we did the same thing. And what is the value you have? Now you have a value about 0.4 volt. 0.45 and 0.4. This is just 0.05 volt. This is not that big deal. No, to us, threshold voltage is one of the most important quantity or parameter of a transistor. So 50 millivolt difference in this transistor threshold voltage, that is a disaster. So you cannot live with that kind of a change. Okay, so therefore, so let's say that we just reduce the channel length. Then why our threshold voltage shows difference? That is a really big deal. If this quantity just kept as the same one, then we will be very happy. But unfortunately, there is a strong proven tendency of threshold voltage variation. Please have a look at this one. This one is taken from Professor Towers. He was actually an employee of the IBM company, and he collected data. This is the N MOSFET, and this is a P MOSFET, and of course, in the case of a P MOSFET, threshold voltage is a negative value, so it should be regarded as this one. It should be regarded as here -2, -0.2, 0.4, and this is corresponding to 0. So this is actually decreasing direction. So anyway, when we have a long channel device, yes, we can well define certain threshold voltage, and let's reduce its channel length. Even when we approach it to slightly 1 point something, almost 3 times or 4 times shorter device, still our threshold voltage is well preserved. However, point is, now beyond a certain position or point, if we further reduce our channel length, then there is a steep change in threshold voltage. So this is a well-known and proven behavior. When you make your transistor shorter and shorter, then now your transistor turned on earlier. Well, what's the problem? So when I use long channel device, I will use, for example, 0.7. And when we use very short channel device, then I will use 0.3 volt as my threshold voltage. So we know channel length, and we know corresponding the threshold voltage. So everything looks perfect for given channel length, given unfortunately, this behavior implies a very serious thing. Here we have a very sensitive behavior of a threshold voltage. If our transistors always, when we try to draw certain transistor, the shortest one, if it provides us 0.3 volt of threshold voltage reliably without any variation, then we will quite happy. But problem is, always we have to consider certain limitation of our manufacturing capability. Although we are trying to draw it, but due to certain malfunction of our manufacturing facility, then we can have slightly longer or slightly shorter device, although we did not intentionally introduce this channel length variation. Then what will happen to your fabricated device? If we are working with this range, then although we introduce a certain process variation, but that does not change our threshold voltage. But when we are located at this quite steep part, then process variation immediately introduce severe change in our threshold voltage. Once again, you can ask me this question. Yes, I understand. Now my device can show, for example, 0.3 volt or 0.2 volt or 0.4 volt in its threshold voltage, although I wanted to have 0.3 volt. But is it really problem? In our case, yes, that is a really big problem, because when you introduce your threshold voltage shift, then what you will have is, when you draw your ID versus VGS, and now let's say that this is the one you wanted to have, and let's say that you have minus 0.1 volt shift of your threshold voltage. It means that although you didn't want to have your curve just parallelly shifted by amount of 0.1 volt toward this negative direction. And unfortunately, that means that when your gate voltage equal to 0, the current you have at this case, that is called as your off current, will show about more than 10 times, almost 100 times increase in your off current. Well, is it big deal or not? This is really a big deal, because that introduces so many problems in your circuit. So simply speaking, nobody can survive with this instability in the or fluctuation in threshold voltage. If our circuit engineers or circuit designers are generous about threshold voltage shift, then as a device engineer, we will be quite happy, but they are not. They are very restrict and they are very stubborn about threshold voltage uniformity. They always say that if threshold voltage changes too much, I cannot design a chip. No, I will not use this technology. That is their opinion. So therefore, we have to provide quite a uniform threshold voltage. So this behavior is unacceptable. So this is, simply speaking, this is the single most important lesson in this entire semester. Threshold voltage should be uniform. We cannot allow this threshold voltage variation. That's it. Okay, thank you, and see you next one.